Modulus. Okay, so that's running. As you can see, there's a lot of material to go through. Okay, so what did we do yesterday? Can anyone tell me? Exterior derivatives. What was the point of the lecture yesterday?
Fundamental theorem of calculus.
Fundamental theorem of calculus. What was another key word that we had to know about?
No.
Clairaut's theorem. What is? No, let me write it. What is the gradient of a function? Is that a one form, a vector field, a function, a set? What is it? It's a vector field. Okay. So we saw yesterday this operator. What's the name of this? Nabla. It takes in a whatever this is. What does this mean? Smooth function on omega. Omega is some set in Rn. And it outputs a vector field. So it takes f and outputs. What is the one form associated to nabla f? Exterior derivative. So, recall by definition, this was fx in the ith direction, fy in the jth, and because you're not scared of 3 dimensions, we can also write fz kth direction. The one form associated to it, remember I always write omega subscript the vector field, and that is just given by replacing I with dx, j with dy, k with dz. So I get fx dx, y dy, and fz dz. This is easy. Right? Everyone agrees that this is rather straightforward. What we're now going to get into is the additional operations that you get on these things that you don't get on these things. Okay? And that's going to be one of the key points to vector calculus. It's something you don't see in the familiar calculus of one and multiple variables. Okay, so here's the name of the game. It's differential forms and exterior algebra. So what do I mean by this? When I write the following, so take, let's say, if I have a vector, I can think of it as a form. Does everyone agree with that? If I take, for instance, the vector 1i plus 2j, so 1 across, 2 up, I can think of that certainly as a form. How do I do it? What would be omega u? Dx plus 2dy. Okay, so for the moment I'll interchange vectors and forms, but really we're talking about forms. So if I have a vector u and a vector v, then what I want to do is I want to have some type of operation which gives me the area of this parallelogram. Okay? Does everyone agree that that depends only on u and v? Because what I can do is take vector u, add v, that gives you this one, take v, add u, gives you that one. Okay? Now the area of this thing is what I'm going to write u wedge v. Okay? Now everyone should be like, what is he talking about? This is absolute nonsense. It's going to be a key property that we need to understand. So, does anyone remember that if we have, let's say, u is AB, v is CD, what what the area of the of this parallelogram would be? What is it? Say again? Modulus of V. You want the cross product? It's the modulus of the cross product, that's right. Another way to think about it is the determinant of the matrix A, B, C. And you would have seen that in 10, 13, 10, 14, 21, 5, 6, something like that. I show it in the notes. For instance, if you want to be convinced that that is indeed the area of the parallelogram, then you just draw this nice little picture. Okay? That's the formality, and this is the geometric picture to have in mind. But one thing I want to do throughout the course is lead our understanding through calculation and then get the intuition later. Because that's how you do it in high school. You know, you calculate derivatives first, and then you learn the meaning and so forth. It would be kind of silly to teach, you know, epsilon delta arguments to year 11 students. Right? Does everyone agree with that statement? Okay, so let's be very concrete. If I have a function, then df is a what? The exterior derivative of a function defines a one form. What I want to do now is make sense of this second derivative. And I claim that's going to be a two form. Okay? We haven't defined two forms, but don't worry about it yet. How do we do it? Well, if I have df fx dx dy, what am I going to do? I'm going to define the exterior derivative of this to be, well, I just look at the functions and take the exterior derivative of those. So I should have x dx, x, y, dy, but I have this dx here. Similarly, I have fyx plus fyy dy. Okay? Does everyone agree so far that this is okay? The key point, the reason why this parallelogram thing is coming on here, is because I need to know how to pair these things here. I need to know what it means to write something like dx or dx, something like that, right? Because you can't multiply vectors. Does everyone agree with that statement that you can't multiply vectors? Yeah, that's supposed to be drummed into your head in 1013 or 111. So what we're going to do is we're going to have a multiplication which essentially is defined like this. What do I mean? I'm going to introduce an operation dx wedge dy, and it's going to have the property that it assigns, you know, I integrate dx dy, right? That's that's like an area integral that you learn in 1116, right? Or 1014. So I want to have some type of parallelogram because I'm integrating over a surface. Okay? But the properties I'm going to claim are that dx wedge dy is minus wedge dx. I'm going to claim that dx wedge dx is 0. dy wedge dy is 0. And it's going to satisfy all the properties I want. If you don't want to understand anything, just understand these rules. Yep.
Just to clarify, dx and dy are being treated as vectors.
dx and dy are treated as forms. When I view them as forms, something to integrate, that's what a form is, they will satisfy the following properties.
The wedge
Okay.
product is defined.
With the wedge product, I'm defining it to have these properties.
Well, that inherently makes sense since the determinant of the matrix consisting of dx and dy is the negative of the determinant.
That's where all the minus signs come in from the determinant. So let me convince you that this is.
And the zeros of the x is the same by twice as the matrix is the negative of the determinant of zero.
I didn't hear a word of that, sorry.
Sorry. The dx, whatever wedge dx is zero because the matrix is not in total sense the same by twice.
It's similar. You take a vector and look at the parallelogram formed with itself, you get a line. What's the area of a line?
Zero.
0. Good. Okay, let me convince you that this is a natural thing to consider. Bear in mind these properties alone. Let u be a dx plus b dy. B is c dx plus, unfortunately, it's better if I write b dy. I know that's confusing, but it kind of turns out to be nicer. This d is just a number, this d is don't get confused. Okay, let's compute u wedge b. Okay, so what's I get? I take a dx plus b dy, wedge c dx plus d dy. Okay? I'm going to assume that it's distributive, so I can expand out in the usual way. So I have a dx wedge c dx, and then have a dx wedge d dy. I'll have now b dy wedge c dx plus b dy wedge d dy. Expanding out. If you're not convinced of the distributivity, you can just read the details in the minutes for an equally misleading outcome. Okay, so remember, if I have forms, I can kind of scale them. I talked about this property at least, not with respect to the wedge product, but I mentioned it briefly yesterday. So what I'm going to do is I'm going to take these numbers out to the front. So I have AC dx wedge dx plus, here I have an AD dx wedge dy. Here I have a BC dy wedge dx, and here I have BD dy wedge dy.
So two of those terms kill each other.
Just one moment. We want to do this nice and slow. We don't have to rush through this calculation. Does everyone agree so far with what I've done? Okay, so now we know that dx wedge dx, which represents the area of the parallelogram formed by x with itself, so it's a line. So this term is 0, and similarly, this term is 0. Now what we obtain is AD dx wedge dy plus BC dy wedge dx. Okay. What's dy wedge dx?
Minus dx wedge dy.
Exactly. So I get AD minus BC dx wedge dy. What's that? Determinant of a 2 by 2 matrix. That's intentional. That's where all the determinants come from. The determinants come from this property. Now, it's not. If I flip it, I take the y wedge dx, then I get minus the determinant. So what's going on? Yep.
It's like a bit too much off right now, but how would this generalize the three?
How do we do it in 3 dimensions? You'll have the volume of a parallel pipette. You know, you take a something of this type. Yeah. And then for n-dimensional parallel pipettes, it extends as well.
You apply different properties to it.
It's exactly the same property, except when you interchange any two of them, you pick up a minus sign. And when you wedge something with itself, it vanishes at 0. Yep.
So I see how AB minus BC fits into the determinant.
Yep.
How does the dx get to the dy fit into the determinant of the matrix?
Yeah. This is keeping track of orientation, which way you go around, right? Now you think, okay, why do I need to consider that? I never consider that when I look at area. But in fact, you do. Because if I take the integral from a to b of f dx, is that the same as the integral from b to a of f dx?
No, the negative. The opposite
It's
direction.
not. You don't, when you look at Riemann integration, you don't look at area, you look at signed area. You've assumed an orientation. You've assumed a is less than b.
So if you would like flip the dy by dx, would that be the same as the transpose of the matrix?
You can do that calculation, and I'll leave that to you. But the key point is exactly that integration requires signed area. Yep.
Does this have anything to do with permutation definition of the determinant, by the way? 'Cause
The permutation definition of the determinant is an unfortunately terrible one. Determinants only make sense, in my opinion, through this picture. Every other picture should be forgotten. Okay. Yep.
In general, if you take a wedge between like two differentials, like you have dx and dy,
Yeah.
can you take like the differential in some arbitrary direction?
I take but any arbitrary direction from linear algebra can be written as a linear combination, and therefore that's exactly what I did. I took a wedge in an arbitrary direction, and then I made vague statements about pulling constants out the front if you just blindly believe that, and then we discovered the determinant while slipping everything over the road.
So if you then take the wedge of any two things that are the same, you're always going to get 0.
That's right. Okay, so what I want to do is I want to get very comfortable. Yeah.
Where did we get the distributed property and also the ability to pull out the...
Exactly, that's a good question, and it's one that I don't want to talk about too much, which is why I have these nice little pictures which pretend to convince you that if you look at areas of parallelograms, those are the properties. So here's my nonsense claim about moving scalars around. You can just scale things. Here's the picture for distributivity. Again, I don't find the pictures convincing, but they are supposed to convince you. And here is the picture for the wedge being 0. But if really, I'm not going to ask you to think about anything in a very abstract way. I'm going to get you to do calculations with these rules. Bearing in mind the picture that it represents the area of the parallelogram, you're just keeping track of, you're allowed negative area in the same way that you're allowed negative area in areas under graphs, I should say. Does that make sense? You should all be a little confused. This is not the most straightforward thing. But I don't think it's so bad. So, just to introduce some more scary words that you can tell your friends. This property is what I call anti-symmetry. For reasons, I think. I mean,
Is that kind of like order relations?
say that again, sir?
Order relations. So they have to be
Order relations.
order.
Order relations.
Because they have anti-symmetry.
What do you mean by order relation? I'm not having any ordering here.
No, I know that. It's just some sort of, it's just a different use of the same word.
If you Google wedge product order relation, maybe someone.
No, what I'm saying is that you know what a law relations are.
I don't.
Oh, it's a relation.
Maybe I do, I just don't know the words.
Transitive.
Okay, we'll worry about it later. So I'm always going to say this is anti-symmetry. This one I'm going to use an even scarier word, but it literally just means this. It means nil. The word is nilpotence. Okay. You will get used to it. So when I say by the nilpotence property, I mean when you square something, it vanishes. Okay, let's look at another example. Let's have the one form omega, which is 2x squared plus y dx plus 3y minus 1 dy. Take eta to be 1 minus sine xy dx plus 2x squared plus 14. What we're going to do is we're going to compute their wedge product. Now, how do you think about this just geometrically if you're kind of confused? You fix any point. If you put in specific numbers, these will give you more or less tangent vectors, right? They'll give you honest vectors if you pass to the associated vector field. And then you're looking at the area of the parallelogram formed by these. But what you're doing is you're allowing it to vary. That's why they're functions. Or one. Okay. So compute omega wedge eta. Okay, so we're going to have, maybe I'll write this for simplicity as P, Q, R, S. So omega is P dx plus Q dy. Eta is R dx plus S dy. Just for convenience. So I now have to compute P dx plus Q dy, wedge R dx plus S dy. By distributivity, I have PR dx wedge dx. What's the next term? PS dx dy. So I did this term, then I did this one. Next one would be QR dy dx.
And then QS dy.
QS dy. Okay. Which terms go away? This one vanishes. Everyone knows what I mean when I say vanishes, right? Equals 0. Because I remember when I took a course in algebraic geometry. Algebraic geometry is a very advanced topic, and they never say equals 0. They always say this polynomial vanishes at an arbitrary point or something. And I remember for like 3 weeks, I was like, what the bloody hell does it mean? It's too embarrassing because it's already week 3 and he's been saying it every day for 3 weeks. It means equals 0. So we're left with PS dx wedge dy plus QR dy wedge dx. Okay. This now simplifies to exactly, so PS minus QR sub this back in, I know that p is 2x squared plus y. This is unfortunate. So 2x squared plus y, that then s is 2x squared plus 14 minus q, 3y minus 1, r 1 minus sine xy. Is that the answer? dx wedge dy. Yep.
Sorry to jump backwards, but over on the left of the board,
Yep.
we've taken d of df. I don't actually get what we've done there because df is a different object to an f.
D of df. So this is, so when you start to present the wedge product, you're on treacherous ground. Because it's so, a lot of people just ruin it entirely. So it's quite delicate how I started. And so I thought, okay, maybe I'll start here. And I started doing it, I wasn't happy with how it was going. So I was going to define the exterior derivative to be exactly this, but I felt that I actually needed to define the wedge product in general first. So I'm coming back to that, and it's actually going to be a big kind of result, which again will rely on the fundamental theorem of calculus and be in there. But yeah, I'll get back to this. This is kind of a definition, in a sense. I have to define the exterior derivative of a one form. I've only defined it on functions. Yep.
The question about the dx plus dy you have at the end. Can you reduce that any further?
dx wedge dy is you think of it as a basis vector. But the vectors are not the vectors on the original vector space. You're now looking at the vector space of two forms. Okay. So it's kind of an indecomposable thing. Okay. So this is kind of the final answer, and that's it. Does anyone have any questions? Don't worry, we're going to do this every day for the rest of our. Yep.
So the form always on vector basis.
You can check that. Yeah. 100%. It's a real vector space. Fun exercises to compute its dimension. Compute the dimension. If you take this is for students who have a free Thursday evening, compute the dimension of K forms on Rn. K forms are dxi1, wedge dxi2, and so on, all the way up to K. So we've only done it for 1 and 2 so far, but you can do it arbitrarily. Okay. That's not a general exercise. Okay, let's look at how we would compute exterior derivatives now. Okay, so here is a list of properties. If you have no concern about its meaning, just remember these properties. Okay? So here's exactly what we saw just then. Let me say that just as a one form was something with dx's and dy's, a two form is something with dx wedge dy, and so maybe I'll also include the following example, which is, let's say, omega 2x dx wedge dy plus 3y dy wedge dz plus 2z cubed dx wedge dz. This is also a two form. The two form on R3. Okay. Just getting used to the language. Okay, so let's look at an example of how to compute something. Let omega be 1 minus sine x plus y dx plus 2y squared dy. So one form, a two form, a function, a set, what is it?
One form.
It's a one form. I want to compute d omega, the exterior derivative of omega. So what do? I take the component function, so the 1 minus sine x plus y, and I compute its exterior derivative as per usual. That's a function, I can compute its exterior derivative. What do I get? Well, if I differentiate with respect to x, I will get minus cosine x plus y. And dx. If I differentiate with respect to y, I get a similar thing. But then, because I have a dx here, I have to wedge with dx. Okay. You can't put dx wedge, dx and dy together, they have to be wedged. Similarly, here I've got, well, maybe I'll put an x here. So it's x plus 2y squared. That will give me dx plus 4y dy, wedge dy. Yeah. I haven't done anything other than differentiate. Notice this is exactly what you kind of do when you do implicit differentiation. Right? You always put a dx after you differentiate with respect to x, dy when you differentiate with respect to y. Okay, so expand this out. I get minus cosine x plus y dx wedge dx. Then I get minus cosine x plus y dy wedge dx. Similarly, I get dx wedge dy plus 4y dy wedge dy. Does everyone agree with that? Who's everyone on the edge of their seat? Yeah, it's exciting, I know. Okay, what's the next step? What happens?
We kill the dy to 0 and the dx dx to 0.
The nilpotence property gives us this is 0 and this is 0. Yeah. What I'm actually going to do is keep the properties. Okay, so that simplifies to the following, which would be minus cosine x plus y dy wedge dx plus dx wedge dy. Yep.
I'm just curious about the origins of the dx wedge dy. So when you go dw equals blah blah, you got the dx in the right brackets. Where did that come from?
Here? Is this what you're saying?
So next one. Next dx. That one there.
Oh, there's an x here.
Oh, right.
I figured that would be the case. I didn't. If I didn't have something with x there, then the question would be why isn't there a dx term? So I put something in, but I need to make sure it's sufficiently large.
And so it's not 2y squared dx. It's just dx on its own.
If I differentiate this term, if I just take the function x plus 2y squared. If I implicitly differentiate that, it's 2x plus, dx plus 4y dy. So that's what I have
Yeah,
there.
gotcha.
I just got an extra wedge to keep track of. Yeah? Yeah.
If you wanted to calculate the values for the answer by studying values of x and y, how would you deal with the dx wedge dy term at the end?
Well, that's the thing. You don't have a form outputs a two form, right? You get if you put in a point, you don't get a number, you get a two form. You get a kind of an area of a parallelogram. Remember that if you wedge two vectors, you get the area of that parallelogram. And what this is saying is that I have a family of parallelograms. Think about it like this. If I have a curve, just think of kindergarten calculus, then we take any point and I have tangent vectors. Okay. Now when I integrate, I really integrate like the area under the curve by adding up all these tangent vectors. Okay. And what I integrate over is like a little distortion. That's like a dx. But what if I have something like a surface? So imagine like a beach ball with a hole in it. And then I want to evaluate or I can pick something more naive or pedestrian, like a paraboloid, and I want to integrate over that. Well, I won't be integrating tangent vectors, I'll be integrating over the tangent planes. In other words, I'm integrating over parallelograms. So that's why we have to do this. And the reason why there's this anti-symmetry property is exactly because when you integrate in the opposite direction in the one-dimensional case, you get the minus of what you would get.
So when you see this called dx wedge dy as a vector, but isn't the area
dx wedge dy is a, well, it depends, it's a vector in what vector space? Right? A vector by definition is an element of a vector space. So it's an element of this vector space, but it's not an arrow in a way. It's a parallelogram. The area is a parallelogram. And this is the reason why we need to do this is because we're now looking not at, the key point is we're looking at function or maps from Rn to Rm, right? And yesterday's propaganda was exactly that vector calculus is studying these things. And so what I need to make sense of is how do I integrate over surfaces? And so that requires having a corresponding differentiation theory and integration theory that handles such things. Okay? What you're used to is you're not used to the thing you're integrating over varying, right? You're used to integrating over a line or a rectangle in R2. Now we're looking at integrating over surfaces and things. Yeah? Okay. Does anyone have any questions? Okay. Let's do another example. I'll do a three-dimensional example. Let's take omega is x squared plus yz dx plus x minus y squared e to the minus z dy plus xyz. Is that a one form, a two form, a three form, integral? What is it? It's a one form. What's the associated vector field to this one form? This with an I, this with a J, that with a K. Two forms you can't associate to vector fields. right? What are you going to check? What's J wedge I? We don't know what that means. Okay, so two forms aren't associated to vector fields. One forms are associated to vector fields. Okay, you'll get used to that. You'll do it. Yeah, you're going to do it every day for probably the rest of your life. Yeah, so. Okay, that's computed its exterior derivative. What is the exterior derivative of this function?
So that to differentiate with respect to x is 2x.
So it should have t2x dx plus
Z y.
z dy plus
Y dz.
y dz right, dx. Everyone agree with this? Okay, the next term should be what?
Some everything's so 1 dx plus minus 2y
Minus 2y e to the minus z dy
plus y squared e to the
and then I differentiate this with respect to z. I should get y squared e to the minus z dz wedge dy. Final term, I differentiate that with respect to x, I get y z dx. If I differentiate with respect to y, I get x z dy, and then I get xy dz, wedge dz. Pretty straightforward so far, yeah? Don't worry, you're going to do 200 of these by next week, and by then you'll be perfectly comfortable. So. Okay, let's expand it out. I get 2x dx wedge dx plus z dy wedge dx plus y dz wedge dx. That's the first term. The second term, I should have dx wedge dy minus 2y e to the minus z dy wedge dy plus y squared e to the minus z dz wedge dy. And finally, yz dx wedge dz plus xz y wedge dz plus xy dz wedge dz. Is anyone confused? Because if you're confused, there's probably 20 people that are also confused.
This is just drawing a red line down the middle of it, like from the top of the bottom left line.
Because now what we'll have is by nilpotence that that's 0, and that's 0. Now, we now just need to keep track of where the minus signs are coming in. What I would like is always to have dx wedge dy, dx wedge dz, dy wedge dz. Yep.
How does the notion of differentiating for one form relate to parallelograms? Like I'm struggling to sort of equate
Yeah,
these
yeah.
concepts, you know?
This is not like I think it's elementary because obviously I do this all the time. I do this for fun. And the way to think about it is, if you're looking at how do I want to start? If you take this thing we've calculated, then if I sub in points, right? So let me make it even simpler. If we just had something like this, let's go even simpler than that because that's a parallel particle. So let's stick to this. This is a 2 form. Now I take in, so let's evaluate it at 1, 1. Then what I see is I have 2 dx wedge dy. So that says that I have my normal parallelogram, your kind of infinitesimal rectangle, or parallelogram. But when I have it at 1, 1, it scales. It's like it doubles. And then you can imagine these parallelograms varying as I move along a surface. I'll give you another example very soon that hopefully will convince you of kind of how these things naturally appear as well. Does anyone else really try to sit with it and do the calculations and get a feel for it? Because it's new. This is, when you first learned how to differentiate functions, I'm sure it didn't just click immediately. Okay. So, I always want dx dy, then dy dz, and dx dz. So, I'm going to put minus signs on those terms which don't have the order I want them to have. So, I'll have minus z dx wedge dy. I just flip them. If I flip, I get a minus sign. If I flip here, I get a minus sign. So I'll have minus y dx wedge dz. Then the next one has the order I like. This one doesn't, so I just pick up a minus sign. And dy wedge dz. And this has the sign I like, that has the sign I like. Y, z, dx, wedge, dz. Okay. So far, so good. And now just collect the dx and dy. There's another dx and dy here. So I have 1 minus z dx wedge dy. Dx wedge dz, dx wedge dz. That's a y, by the way. Yz minus y dx wedge dz. And finally, I'll have xz minus y squared e to the minus z dy dz. Okay? That took us it may seem like a very long process, but you will get very quick at them. I already recorded a video. I can't. Let me. If you look at the, oh my god, that picture is terrible. This first video, computing the exterior derivative of one form, goes through another example of this. Okay? So progressively, what I'll do is I'll upload these board recordings to the channel as well. And yeah, while you're there, you can subscribe to my channel, like all the videos and so on. I teach these courses to build the channel, if that's not clear. What was that, sorry? The only course I teach? This semester, yeah. Next semester, I have no idea. I have no idea what's happening. So if we look at feel free to leave a negative comment. Everyone seems to do that on my channel. Everyone likes to give me their opinion on how the video should have been done. So feel free to do that as well.
Surely do a 5K subscriber giveaway.
Yeah. So.
I don't think, like, you enter, they often, YouTubers often say, subscribe and win a free whatever. Maybe you could subscribe and win a free 10 marks.
A free 10 marks. Well, we'll see how many. If you can get this to 15,000 subs, then I'll think about it. For this course, vector calculus and differential equations, that's the playlist. Bear in mind, some of these videos are rubbish. Some of the music is absurdly loud. I apologize for that in advance. Just read the comments to check if the music is too loud. But let me also add that my introduction to vector calculus video, the music is a bit loud, but more or less it's okay. I use the word conservative vector field. I'm not going to use that in this course. Conservative vector field is gradient field for us. Okay? I recorded that video before I wrote the book, and when I wrote the book, I decided not to do that. Okay, so everything should be called a day. Okay, that's my plug. So we have a reference if you're confused. There is a video which explains how to compute exterior derivatives of one-forms. How are we for time? Okay, I need to take a 5-10 minute break. So, okay.